So this first task then, we're going to look at this simple bracket. We're going to do a couple of things to it. We're going to optimize this bracket because we're going to see about adding some forces onto here, and we're going to simulate how this would act, how the forces on this would act. And then we're going to see if we can reduce the weight and optimize the bracket a little bit as well and see what the difference is between each of them. So just basically created a quick and easy bracket. It's quite large and it's got a thickness of 2 millimeters, so just a piece of sheet steel. And we've got the two holes in the side, two 16mm holes. So this can then bolt into something else, another bracket on a wall. So first thing then, just looking down their little table, first thing I want to do is take a weight of this part. So they're all plain carbon steel. I think I've shown you this in the classroom before. So I'm going to go to Evaluate and Mass Properties. And then if we look down the mass properties, we've got a mass here of 823 grams. Okay, so 823, let's write that in there actually. 823 grams. We're going to apply some simulation to this now. So in this software, we really don't have a lot of options. However, let me just pull up this Simulation Express. This is some very basic simulation software. Thankfully, it comes up with this little guide to start you through. I'm going to hit next. So the first thing that I want to do is to say which parts of this model are going to be fixed in a location. So the fixtures are going to be where these holes are here. If I click on the inside of these holes, those two, they're listed down here on the left. I'm going to hit the tick. So that means that they won't move. So whatever force or pressure I put on the top here, those are going to be fixed in their location. So I'm going to hit next. Then we're going to add a pressure this time. Because this is a shelf, there's going to be a constant pressure sat down on this top lip. So I'm going to hit add pressure. And I'm going to select the top. And we're going to put a pressure on of 10,000 newtons. Does anyone know how much that is in tons? Any idea? Let's just quickly look. So 10,000 newtons into kilograms. 10,000 newtons into kilograms is, yeah, so about 1,000 kilograms, so just over a ton. Okay, so that should be quite a nice sturdy bracket. That's all we need to add on here. If we were in the full version of the software, we can add some other bits and pieces to it, but that's pretty much it for this. These simulations are basically just to give you an idea of how your design's going, rather than to give you exact data. So we've got a material, we've got a size and a shape, we've got some fixed locations, and we've got a pressure. Okay, so I'm going to hit next. So our plain carbon steel, which is the material we selected, it shows us the Young's modulus and the yield strength. And we're going to run the simulation. Should only take a few seconds. And obviously, depending on how much RAM you've got on your computer will depend on how fast that simulation runs. Okay, so you get this little animation which is showing the deformation or displacement. I'm going to stop the animation because it doesn't really tell me a lot. What I'm interested in is the uniform displacement, and I'm also interested in what factor of safety we've got. So down the left-hand side here, let's call up the stress. So this is showing me the stress of this part, and I can use this then to analyze which areas have the most stress applied to them. Okay, so we can see just at the top here of the bolt hole, There's a little bit, and it's just going orange around the bottom of this one. And then you can see, obviously, the blue and the green as it changes. Blue is the least amount of stress, and then obviously red is the most amount of stress in that part. So still, that doesn't mean a huge amount to me. Let's have a look at the displacement. So the displacement this time is just showing the maximum displacement of the part. And although it looks a lot on this visualization, we're talking points of a micron, really, really small. Okay, so 2.2 times 10 to the minus 4 millimeters. So it's really small amounts, and this is obviously showing it exaggerated just to show you where it is actually moving and deforming. If I now click into factor of safety, it's currently all blue, and that is telling me that anything that's red is under the factor of safety of 1, and anything that's blue is over the factor of safety of 1. If I hit this continue button, it will actually tell me here my factor of safety. So does anyone know what that means? Anyone know what factor of safety is? Okay, so it's the ratio of the structure's absolute strength to the actual applied load. So if it had under 1 factor of safety, what that would mean is that our part, with the load that we put on it, with the 10,000 newtons, wouldn't actually work. It would break itself. So we always want stuff over 1. Usually when you design a part, you'll try and aim for a factor of safety of 2. We've got a factor of safety of 1,209. Okay, so I'm going to stick 1,209 in that box. So we're well above where we need to be. And then the uniform displacement is the displacement. It's that URES value. Put in there 2.253 times 10 to the minus 4 millimeters. Okay, so quite easy to apply, and you can stress test pretty much anything you want. You just need to know what forces or pressures you want to put on it, and then what elements of it are fixed, and know what material it is. And that's all you need to know. Okay, so let's run this again, but we're going to run it now for a weight reduced part. So we'll see how much the weight comes down on the next one. Sounds like somebody's underwater. Okay. Let's bucket. That's the one we want. So here's the weight reduced part. Okay, same thickness. Not done anything else to it. I'm going to go through the same process. So simulation. Hit next. So we're going to add the fixture first. Same bracket again. And then we're going to add the same load on top. Hit the tick. Go next. Same material. And run the simulation. Okay, so we can see now it's deforming in a slightly different way. Okay, so let's stop that animation. Let's have a look at the results. So let's look at the stress. So we can see that actually now the maximum stress now is moved into this corner as opposed to here. But we've got a bit more stress up around the top and a little bits on the bottom. So again, not a huge amount. Okay, and it's all staying quite nice. Let's look at the displacement. So now we've moved the most amount of displacement from the front to this middle bit here. So that would tell me that this is probably one of the weaker parts of this model. Okay, so let's stick the displacement in. So 1.234 times 10 to the minus 3. So although that looks more on the displacement, it's because it's a lot more. Okay, and let's check the factor of safety. Should still be well within what we wanted. And the factor of safety now is 287.92. Okay, so let's take a quick weight. And we're now 478 grams. 79 grams. So we've nearly half the weight. However, our factor of safety has come down significantly and the displacement's increased. However, we're still well within our factor of safety of 2, which is an ideal value. Okay, so we're going to do it one last time for our final model. One last time for the final model, which is the fully optimized model, which is this one. So it's still plain carbon steel. Let's take a mass, 217 grams. Don't want to force, we want to pressure. And that's 100,000. Okay, you can still see the displacement. So the stress in the part. So a little bit more up here, a little weaker area, a little one down here. A little bit around here as well. Let's pick our maximum displacement up. So we are 3.476 e to the minus 2. And then finally, factor of safety still looks well within. So the factor of safety is now 38. Okay. Okay then, so anyone still there?
Yeah.
Just about.
Just about, yeah. Okay. So if I said to you right at the beginning that my initial design of my part to hold this just over a ton of pressure on a 2 mil thick plate, and I could reduce that right the way down to that, would you have expected that to have worked so much? I would have questioned it.
No, I wouldn't. Looking at that design.
No. And that's what this is for. It's just it's to help you look at the design a little bit and say, well, okay, is that over engineered? Can we reduce stuff? Now, there's a little box under here. For you to have a little think about this and think about how the design could be changed in light of this data that you see. So one thing that this hasn't picked up, and I tried to allude to it a few times, was pulling the part around this way. So it's not taking into account any buckling that might go on. Okay. So this part, before it would break down this way, down this axis, it would twist and buckle because there's less material around here. And unfortunately, this basic simulation doesn't take that into account. Okay. Does that make sense?
Yeah.
Yeah.
Yeah. Now, if we have the professional bit of software, there is some more options, and the simulation that we run could include buckling. And we'd actually see this buckling in 3 dimensions. And that would massively change the data that we've got. Okay. What about part cost and manufacturability? Is there any difference between these 3?
Wouldn't that be cheaper? That'd be more.
That'd be more expensive.
Yeah.
It would be less material, but probably more expensive to make because you've got to cut the holes out. You've got to cut these extra bits.
You've got stamping and machining on there, but then you could look at, can you get more pieces out of a sheet because you've got that cutaway section in the between the angles?
Yeah, indeed. Yeah.
So the material usage as well.
Yeah. What if you put a radius up in this top corner, because most of those simulations didn't show much stress up here.
Yeah.
So that radius would sit a little bit closer in here, and you'd get a bit better sheet utilization again.
Yeah.
Yeah.
Yeah. So that's kind of what this wants to inform you of. Just that there's some basic data you can take from it, but ultimately it can help empower where your design goes. So would I design that bracket ultimately out of 2 mil thick sheet of steel to hold a 1 ton pressure? Probably not, because of the buckling that I think would go on. However, if the pressure was directly down on this and there was no buckling to take into consideration, then yes, actually it's over-engineered still. What else could we do to that, do you think?
As for a lightweight racing caravan, that one though.
Indeed. Let's not stand under it.
No.
No.
Probably make it thinner, couldn't you?
Change material.
Yeah, we could change the material. Now, the reason I chose the plain carbon steel is because out of the steels, it's one of the weaker ones. So, well, we wouldn't want to cast it. The cast alloy, there is this alloy steel here. The tensile strength is quite a lot higher than the where were we? The plain carbon steel. So tensile strength's nearly double. So, you know, if we were only considering that direct force coming down and we knew there was no buckling going to go on here, we could probably get down to plastic on this. Should we try one out of plastic? Just run a simulation? Let's have a look. Let's do ABS, which is quite a tough plastic. Let's just quickly run this. Hopefully we can get it to break. Well, okay, so it's showing a deformation again, which we expect. Let's, oh, it's not come up with a factor of safety. Go. So now that's, let's have a look at that displacement value. So that's actually now moving 3.7 millimeters. That would probably be enough to break that somewhere up here. Maybe,
Is that why
maybe
there's
not.
no factor of safety?
There's not come up with a factor of safety. Let's just see if it pops up here. There we go. So based on the parameters, factor of safety in your design is 0. Don't know why it's not coming up and showing me, but that basically tells me that yes, this would break under that pressure. I don't know why it's not brought it up down here, because even if it breaks, it comes up, and you can often see the different parts of the design that would break and the parts that wouldn't break. So I wonder why that is. Anyway, we won't worry too much about it now. And again, it's only considering that in 2 directions as well, 2 dimensions, so just straight up and down, no buckling going on. Okay, so yes, that displacement was quite a lot, wasn't it? 3.6 millimeters, which is expected. Okay, so that's some basic static testing, some stress testing. And just show you some optimization as well. Again, don't use all this data verbatim, but it's a guide. It can show you where you've clearly over-engineered, and to hold a ton of weight, you know, that's clearly over-engineered, massively over-engineered. What else could we do with it then if we wanted to reduce this down? Any ideas? I suppose we could change the thickness. We could probably change some of these dimensions. Now, I'm just going to scroll on down. There is part of the software here in SolidWorks that does something called Topology Optimization. Any of you heard of that before?
No.
No? So basically, topology will enable me to tell it the things on this model that are fixed that I can't change, tell it things that I might be able to change. Let's say I could change the length, or I could change the height, or I can change this, and I can set up a bunch of variable parameters. And based off the simulation data, SolidWorks will go through this part and all your variables, and it'll find the best solution for you. Really clever little bit of software. Unfortunately, it's not in this version that I've got. I've been looking all morning to try and get it in. So I put a couple of links for a couple of videos. So I think it's really important to have a little look at that, because there's a lot of things that can do. Okay. Anyway, everyone happy with that one? This bit of statics.
Yeah.
And what benefits it could bring.
Yeah.
Let's jump down. Okay. Okay, so the next one we'll look at then is some assembly motion simulations. So we're not going to simulate any statics with this or run any specific simulations. What we're going to do is just check over this assembly. So this is a little assembly that a student made a couple of years ago for me. And it's a little machined vise. And I thought this would be good just to show you a couple of things that we do with this. Okay, so this can work on any assembly, and it will work in all the versions of SolidWorks. So we're just simulating the movement, and what I've put in here is a mate, which is how we stick the parts together, just to say that you can move so far away from there, and then that will slide in so it just touches. Okay, so this is kind of simulating the motion that we can have in a part. And you probably can't see, but I can turn the handle, and the handle turns around, and these other parts are stuck in their positions. Okay, so benefits of this. We can do a few evaluations. What would you think we'd want to check on this to make sure that when we make this, it's actually going to work? What do you think?
Well, that it slides up and down.
Yep, so my model slides up and down. What about if we, let's pull this right the way up here. So this little bottom plate. So can you see that bottom plate there interferes with that radius corner?
Yeah.
So
some clearance.
Yeah, so this would only go up to about here if we actually made this to those sizes, and you can see there's a gap now in the side of here. So one of the first things we can do when we've got a model together is do interference detection. So I'm just going to click this button. It's selected the whole assembly, and I'm going to hit calculate. And that little ping tells me that it's already calculating that inside here, in that red zone, there's an interference somewhere. Okay. So if I select these two, so that's between this bottom runner and this plate that's sat on top. Let's hide this one a second. There we go. So it's actually interfering with another bit that we didn't even notice. So this cutout stops before this one. So in the position that we were in, it was creating that interference there. So let's pop it all the way up and do it again. There we go. Now it's come up with 3. That's what I expected it to do. Okay, so it can show me these red zones are the zones that we've got overlap. So that's the one that we looked at. That's the one in the other corner. And then we've got this bit in between here. Well, it's just shown that there's an overlap. So I can then go back into those parts and make some edits to them, just to make sure that when we actually make this, we're not going to have any of these physical issues. I've worked in a machine shop for many years, and I wish the designers utilise this, because we've spent loads of time fettling things to get them to fit, especially on prototypes and one-offs, short production runs. Okay, so really quick and easy tool. I'm not going to amend them as we're here. I'm just going to go through these couple. There's also then clearance verification. Let's just put clearance in there. And you can check, because obviously if you design stuff to be face-to-face, you're going to end up potentially with parts that are not going to fit because of your tolerancing. So you're always going to have tolerancing in, and this clearance verification can help you verify that you've got tolerancing correct. So I could build a part and add my tolerances onto the part, and then in this clearance verification, if I had tolerances on these parts, which I've not got on these, it would actually check the maximum and minimum sizes to see that they fit together. And you could then amend your tolerancing if you need to. Okay, and there's one more tool here which is useful, which is hole alignment. And again, I'm just going to hit calculate, and it will tell me if any holes are have any deviation in their alignment. So this one here is telling me it's 1.7 mil out. So if we scroll around the back, we can see that those holes are not quite lined up. Okay, and the same in here. Those are okay, which is why it's not pulled it up. And then finally, something to do with this hole at the top of here. It's not sat in this part properly. So again, I can go through and just check those, go and have a look at why that is, and get it right before we decide to ask anyone to make it. Okay, that's pretty much all I wanted to show you in here. Okay, so just some interference detection. Really useful for making sure that your assemblies work and that they are not going to have any problems when you've actually made this physically. Okay, so it's an error proofing software, part of the software. Okay, any questions?
Can you import standard designs from other manufacturers, say sort of gas struts and things like that?
Yeah.
Will they have the correct properties brought in that you can then test in your designs?
It depends how they're made.
Yeah.
To be honest with you, it depends on how well the initial parts are made. If they're from a supplier, then I would normally suggest that yes, they're made correctly. So I'm just jumping into this design library here. I used to load this up when I was a design engineer with all the parts that I frequently used. So yeah, cantilever clamps.
Yeah.
Used to use all variable sizes from the one manufacturer. I got them to send me a model of each of them, which they had for their manufacturing purposes. And I just put them in a library here and I just drag and drop them in. So as long as they've been made correctly as solid objects, then yes, you can apply all of the stress, all the testing, all the verification with. You start getting into problems when you get people uploading models as surfaces, and not solid objects.
We've had that problem before because we've tried to put clamps and linear bearings in and they've not worked in simulation, and it's because they've been a surface, not a solid object on their own. But that was in that's in CATIA rather than SolidWorks, and the simulation in CATIA is not very good. No,
and to be honest with you, the data that you'd get in SolidWorks probably isn't great either. You know, if you're really wanting to rely on the data, then you know most people will end up buying a specialist software to do the simulation. But the whole point of this is just it can give you these indicators at the beginning, as you're designing these products. So I find SolidWorks has got their own site called Content Central, and there's loads of supplier information on there, models, tens of or hundreds of thousands, and you can just download those to use as well. You think that's a good thing for a supplier, because if they've got all of their models accessible to designers and you can just pull them out and drop them in and set a few parameters, then you know that should be good for them, because you can ultimately just go off and order those parts then straight away and you know that they're going to work. However, as I said, some of the models, and as you've experienced, Andy, some of them are made as surfaces. I'm not sure why people would do that, because for me, surfaces are often more difficult to make. I suppose it depends how you've been taught, isn't it? And This was direct from a supplier, so I don't know quite how they managed to manufacture them when they got to doing what they were doing. But subsequently, we didn't use that supplier. Indeed, and I've had exactly the same experience. I was actually pulling some bearings off, and I actually got the models to work with the bearings, and then I ordered the numbers, the part numbers that were on the bearings, and when they come in, they were slightly different. So it was the last time we used the supplier. Answer to your question, you can use all of that stuff in all of these different elements, however you wish. So on here then, so we'll just look at the interference, clearance, verification and hole alignment, make some suggestions on how this could be improved. So or really the benefits of it, to be honest with you, on this one. And we can quite easily see where there's some problems with the parts. We can go back and design them. We can test them and just keep rerunning these couple of different ones just to see where we are with it and whether it's actually going to work. And again, it's a good error proofing, thing. So okay, let's leave that one there. I'm just gonna take 2 minutes. I'm just gonna go and grab a drink because my throat's gone very dry, and then we'll have a look at this little puller frame. So a proper object now, part of this little bearing pulley. We're going to stress test this as well, and we're going to see if we can improve the design on it. We actually have a factor of safety that's close to where we want. Okay, just give me a minute and I'll be back.
Yeah. Play random lift music if you want it.
So we're using these examples for a part of our assignment, are we?
I don't know. I don't think so.
Or is he just demonstrating?
Just demonstrating and then bullshit your way around it into the assignment, I think.
So we've got to download this SolidWorks software and actually use what he's doing. Is that the idea?
I don't know, to be honest.
Hello, I'm back. Was that a question?
Yeah.
Sorry, go on.
Go on.
All right. Are you expecting us to download SolidWorks? And is this like a tutorial on how to use it?
No, this is I'm running through these models, George.
Yeah.
And we've got this little worksheet, and I'm also recording this, I hope. So this is kind of trying to get away from using the software.
Okay.
So these are things that I would have done with you in the class or something similar to show you just what these software can do. So I'm trying to get around you actually using it. So
Right, okay.
Ultimately, the answer to your question is no, I don't expect you to download SolidWorks and do all of these models and testing. However, I will need you to fill in some of this lab sheets based off what we're doing now.
Okay, so we're using the data, we drag it out from this lesson,
Yeah,
and putting it all into our thing.
Exactly it. Yeah. So that's why I'm recording it, to make sure that it's accessible after as well. So yeah, it's kind of me showing you roughly what this can do, pulling out a bit of data, because what I want you to be able to do is to be able to look at the data that we're generating and then make some valid considerations off the back of it for the design.
Right. Okay. Yep.
Okay. So yeah, so this is what I've been battling with Pearson's over, is the fact that, you know, you guys are probably not going to have access to this, and even if you do get access to it, because you've missed so much teaching, you're going to struggle to do this.
Yeah.
So the suggestion was that we do this live lab, and record it obviously, and then you can come and analyze the data and just go through how this would work. I think the very final bit of this lab sheet, I've asked you to, there you go, just consider how you would use this on the parts that you're designing. So I don't expect you to actually do it. Okay. Just have a look at what we're doing and then think about how any of this can actually apply to your product. Is that clear, George?
Yeah. Thank you.
Okay. Okay, so we're halfway through. And right then, let's crack on with this last couple of bits. So we're going to do something very similar in this one. We're going to look at doing a little static study on this little frame for this bearing pulley. and we're going to have a look at a couple of different materials on this one and have a look at the factor of safety for each of them, pinpoint the displacement, maximum displacement, uniform displacement, have a look at the factor of safety and see if we can come up with a suggestion of material to actually use. Okay, and then after that, how can you alter this design considering the factor of safety, weight, material, manufacturability, and any other physical factors that would change this, how this part would work. Okay, does that make sense?
Yeah.
Yep. Okay, good. Okay, so let's do a static study on this to start with. So got plain carbon steel, which we'll start with, which will be our first material. And we will go through. Sorry, because my screen's small, it's missing a couple of buttons and it's throwing me. Okay, so let's start over. Start from scratch. So we're going to add some fixtures like we did last time. In this case, it's going to be the center of the part. So this is going to be the fixed point, and then these end bits are going to move off the back of that. We're going to add a force this time, and we're going to apply a force into all of these holes, just the front ones. Okay, and what we want this time is, can you see the force is circular within here? It's acting in all directions. What we're going to do is select the direction, because if you look at the pulley over here, this is going to be pushing up or down once this goes pushing in. Okay, so let's select a direction. And I'm going to use a plane. So I'm going to select the top plane. And there we go. There's the force acting up. Let's reverse it. And we're going to stick 4,000 newtons on this one. Okay, so I've got a 4,000 newtons coming down through the holes. And the middle part is fixed. Okay. And choose our material. So let's start with the plain carbon steel. Hit apply. So there's our modulus, Young's modulus, and our yield strength. And so Young's modulus. So 220.6. Okay, let's go next. Run simulation. There's our displacement animation. Let's have a look at the stress. So again, one of the things that bugs me slightly in this software is that it always changes the scale of your stress. So when you're trying to compare variable things, it can be difficult sometimes to figure exactly where you are. So it amends this and changes it relative to how much stress is in the part or how much displacement is in the part. Okay, so there's our stress. We can see a couple of little weak areas, under the bottom here. Let's look at the displacement. So there we go. So displacement is around, what's that, about half a micron. Let's put max URS in. There's our deformation. have a look at our factor of safety. So it's currently calculating on a factor of safety of 1. Let's change that to 2. Just want to make sure this is okay. 2. Done. Okay, now this is odd because this should be under one is red. Why is this not updating? Ah, there we go. Okay, so now it's showing a factor of safety of 2, and all of the red elements are where we are under our factor of safety of 2. Okay, so we can see that there is potential for this part to not reach its factor of safety. Let's put 1 in because it does say here that it's 0.9. So somewhere on this model, there it is, there's a little part of this that if we get up to putting 4,000 newtons of force on here, it's potential that these elements could start splitting. So let's type that in 0.9.
Wrong box.
Oh, wrong box. Thank you. 9. What do we say? 0.93. Okay, so there's some errors here which show that we wouldn't really be able to get up to 4,000 newtons using plain carbon steel. It was plain carbon steel, wasn't it? Yeah, let's type that in. Okay, I put maximum displacement and max URes. Those are the same things. So shall we put, let's put maximum stress in there instead. So maximum stress 2.365 plus 8. Okay. Okay, so what we want to do now then is just try this with a couple of different materials to see if we can get this factor of safety to meet 2. Okay, we want to get rid of these red areas on the part. Okay, so let's done viewing those results. Next, let's go back. So I'm going to run through it all again, but this time I'm going to change the material.
It's going up, isn't it?
Sorry?
You got it the wrong way around. It's going up, isn't it?
It's not going where I want it to go. That's for sure. Right, let's see if we can edit this. Edit definition. Yeah, pick the wrong plane. Thank you. Let's check. There we go. So that's going down. Yeah, there we go. Okay, so add a force, add a pressure. Let's change the material. Should we do this alloy steel next? Right. Okay, so Young's modulus, same. 6, 2. 0.4, and let's see what this does. information. Let's have a look at the stress first of all. So same areas that are weak. Our stress is the same. Maximum stress is the same, obviously. Probably why I didn't put that in there before. Let's look at the displacement. This should be different. Displacement's exactly the same. That's strange. I would have expected that to have varied. Let's look at the factor of safety. Okay, factor of safety is now 2.623. So the factor of safety is exactly the same. But isn't that strange that the displacement's exactly the same? Okay, let's go back. Let's try another material. I'm going to see if I can go back this time, save having to do everything. Change material. Should we do a stainless steel? Let's do a 3. Let's do this American 304, which I believe is a stainless. Okay, let's look and see if our stresses are the same. Slightly lower.
Yeah.
Yeah. It's not giving me an exact value. Oh, there it is. Yield strength down the bottom. 2.06. Okay, let's look at our displacement. So actually more displacement. And let's see what our factor of safety is. So factor of safety is lower now. Okay, 0.875. And if we look underneath, yeah, those same little areas. Areas are red. Okay, let's go for, oh, I didn't jot the values down. I'll jot those down now. Let's just go back. Back. Here's modulus 19. Yield strength 206. Okay, let's change the material final time. Should we try a cast one? Let's try the cast carbon steel. Okay.
Two, 4, 8.
Run the simulation. So yield strength 2.482. Need to plus 8. Maximum uniform displacement 6.065 e to the minus 2. Our factor of safety 1.53. Okay, so there's our bit of data. So quite clearly that alloy steel with its high yield strength is giving us the strongest part. And none of the others are actually meeting our factor of safety. Okay, so what I'd like you to do when you fill this in is just put a couple of sentences in here just to analyze some of this data, see what conclusions you can make from it. And then again, what design suggestions would you add to try and make this part better? So I think for me, there was one key area on all of these that was a little bit weak, which was under here. Let's bump that up to 2. That should show us. Come on, go to 2. There we go. There's this one weak area down here all the time. So is there a way that you could get around or make that little bit a bit stronger? That's where it's always going to break. Just across the top of here as well, maybe, but I think that bottom point there is where most of the stress is coming in. So again, if this was me making this part, I'd be trying to make some decisions on how I could improve that. Can I move that stress a little bit further away? Can I do anything to, let's go back onto our stress. Let's see these blue zones here. These blue zones have got very little stress on them, so can I do anything with that if I was looking at weight reduction? And then all the time having to still consider the part's manufacturability. How am I actually going to make this part? Am I, by adding some cutouts in here, which I could quite clearly do through this little cross section, is that really going to give me any benefit once I try and manufacture this? So if I add complexity into my manufacturing and into my design, is it really going to give me a benefit? Okay, any questions off the back of that one?
No.
It's probably the most useful one we've looked at so far because it's a real part. Okay, so again, a couple of bits there, and finally, I was waiting for a chair. No.
Sorry, just going back to the last one then, just a quick question.
Go on,
So that crank pull or flywheel pulley puller, you've got the fixed point in the center, and then you've got the force acting at the ends of the arms.
Yeah.
Can you have two opposing forces in that then? Because technically, in use, the fixed point is the pin that goes through the middle.
Yep.
And that's on a threaded. It's a threaded bar with a mating thread inside the part, which is pulling the whole thing up. So you'd have an extra point of stress where the threads are.
By all means, yes. So
pushing out, don't it, rather than in?
Yeah.
Yes. Yes. So yeah, again, you know, it's just, this is trying to just show where there's potential for some areas. If I had this whole design and I had the better version of this software, because this won't actually do assemblies, it will only do individual parts. But yes, I have that whole assembly, and I could put all the forces on it exactly where they are, and you can you'd be able to increase the force coming up into here to simulate that tightening and tightening, and you will see all the elements that you would need.
That's more what I was asking, really. Does the student level of the software allow you to have assemblies and the two different forces, etc.? Okay.
No.
Fair enough.
Not for simulation.
No,
the version that we've got at college is the full version.
Yeah.
So yes, you can do all of that. Obviously, this is just a stripped down version, which has given us the bare basics, really.
Yeah.
But yes, you can definitely do that with it. Okay.
No worries. Thank you.
Awesome. All right. Final one. We're going to look at some aerodynamics. I'm going to do some flow simulation. So we're going to have a look at the little race car here. Let me call it up. And race car up. There he is. So although this looks like an assembly, these wheels have just been added in as part of the main model, just so we can see how these are going to work. So again, we're going to look at some basic aerodynamics, and this is very basic compared to what the full version does, but again, it gives us some data we can look at. We can make some suggestions and improvements. So rather than starting here where I've got a complex shape, I'm going to run the simulation a couple of times, and I'm going to start basically with the first part of this. So let me just show you how I've set this up. So let me suppress those. So I've basically deleted all these features, but I've not deleted them. I've just suppressed them. So they're still there, but I'm not using them. So we're going to look at the aerodynamics on this block of material to start with. Now, when you do flow simulation in SolidWorks, you can select different materials as your flow property. You can see how temperatures vary through your simulation. You can see how the material changes as it interacts with different objects. You can test pressures and all sorts of stuff. And once again, it's coming a common theme. In this basic version, we can only do a few basic things, but I can get this simulation to work and just show you what's going on. We've got this block, and at the moment it's inside SolidWorks, which is an infinitely sized space. So the first thing that I needed to do is to create an enclosure to put my model in. So I'm not really interested in the air in front of this model, too far in front of this model, just a little bit. I'm interested in the air at the back, and I think most of the data is going to be within this box. So the only thing you have to do with this box is make sure it's hollow, and then you have to cover the ends as well, which is a bit odd. So make a hollow box or tube, and then close the ends off. Okay, so my part's inside this little container. I'm just going to hide the container because I don't particularly want to see it. There we go. And I've got this balsa block, just a block of wood, which is quite small. There we go, 50 by 65 by 200, 223. And we're going to do, this time, we're going to look at a flow analysis. So it's this second box in. So this is where we've been doing our statics, and this is where we're now going to look at the flow. And again, this will talk me through a couple of little dialogues. Did you see that nice big menu pop up and disappear?
Yeah.
That's all the options that I could select, but in this version, so it must be there, and they've just blanketed it over in this version. So I'm just going to go back to the start of here. So I've only got a couple of options that I can fill in with this one. So I'm going to use air. So we're going to see how this goes through air. We're going to tell it that we're looking at the volume flow rate, and I've given it a value. I say I've given it a value. This has come from another tutorial. There's a temperature value, which is about 20 degrees C, so 293 kelvins. And that's acting on the front plate. And acting on the back plate is atmospheric pressure. That's all that is. Okay, and what we're going to do is we're going to see how the pressure varies from the front to the back, and we're going to trace a couple of lines with it as well. Okay, and that's it. That's all I need to do to set this one up. So I'm going to hit solve. It'll take a little bit longer because it's calculating more data, or it might take a bit longer. It's basically going to give us this little image here. There you go. It's giving you some little ideas there. Look at some of the things that can be done with flow. Mapping temperatures and airflow and water flow and cooling, as well as the aerodynamics. Okay. So what we've got down here then, we're looking at the trajectories. I'll press play in a minute. There's 44 of them. And up here we've got the velocities. So we've got a start velocity, which is around 30, 40, somewhere around there. I can't remember what we put. And then as the flow goes through, if there's no interference, the flow should relatively stay the same. As the flow hits the block here, we can see that the airflow slows down and then speeds up around the corner and then slows down again as it goes around the side. Any ideas what would cause this slowdown around the side here? You'd think once it goes around there, it would just speed up.
The friction.
Friction? Friction with what?
The material, I don't know.
Well, it could be friction with the air itself, because any air in here is now compressing. But yet it could also be friction of the block itself as well.
Is it a change in temperature of the air?
There would be a change in temperature, yep. So all this is showing me is the velocity change. However, again, on the full version, I think if I scroll down here, I did show this. There we go. You can actually show, I didn't put it in there, but yes, you can show the temperature changes, the rate of temperature change. You can show friction changes, all the different forces and all the velocities. And all we've got up here is these couple of velocities that we can look at. So anyway, let's look at this. I'm going to change these figures on here so we get a uniform set of figures. I think it just helps show the data a little bit better. So I'm going to put 20 on the bottom, and we'll go up to 60 at the top. Okay, and we can, for me, that's a little bit clearer. So you can quite clearly see at the front of the model, we're down around the 30s. And then it speeds up a little bit, speeds up considerably going around the side as the pressure increases and it gets forced around. And then as it goes through the model, the pressure drops a little bit. And you can see, obviously, you can see that quite clearly. So there's a lot of friction going on here. The trajectory is changing a lot, the speed's changing a lot, and there'll be a lot of heat. So there we go. That's the actual models moving. Okay. So what can we observe off this data with this block? Any ideas?
It's not very aerodynamic.
Yes.
It's not very aerodynamic. Yes, exactly. It's probably all we can deduce from it. But yes, that's basically it. It's not very aerodynamic. We can see that actually the air pressure, the pressure difference is over half the velocity at varying points. And lots of red in there, so we can see it's really not very aerodynamic. Okay. So let's add a little bit more in. So let's add a couple of these features. There we go. So we've got a slightly more aerodynamic shape. This little race car, by the way, is off a little competition that SolidWorks used to do. They don't do it anymore. With a charity called F1 in Schools, and basically it's to design one of these little cars, run some simulation on it, and do some other bits, and basically a mini race car challenge. Anyway, so we've cut a little shape in the top. Should that help our aerodynamics now?
Yeah.
On the sides. Yeah.
Yeah, down the sides. Well, one of the other things that one of the key things that to consider is this frontal area that you have, this contact area, and we've now reduced that significantly. So hopefully our data will look a little bit nicer. So let's go through this again. Unfortunately, I've got to run this each time I make a change. So it'll take a few seconds again. Now, again, if we had the full software on here, you would be able to map individual trajectories. I'm just going to make this image bigger. You could actually map individual trajectories and you could see how the air is simulated to flow behind it. So on this, yes, it's shown a little bit, but when the flow streams are much smaller, obviously you can look at things in a lot more detail. Okay, so hopefully this one's nearly ready. Okay, so there we go. Let's change our scale back to where we had it before. So 2060. Is it 60? I think it was 2060. Yeah, 2060. Yeah. Okay, so there we go now. Consider how much red was on the last one. And we can see now that it's not a massive amount of difference. With the velocities now, it's a little bit more consistent. So we're looking up towards this higher end for most of it. We're not going right up to the red, which means that it's not compacting massively, apart from around this side of here. And just little bits of orange, a little bit of blue coming out the back end of here. And that's probably from that one stream. Yeah, going down there. Okay, so we can see that the change in shape then has made a fairly substantial difference to the aerodynamics of the part, the car. Okay, so let's go back again. Let's add in all of the features. Actually, I'm not going to add in quite all of them. There we go. So I've put some wheels on now, and obviously cut this bit out across the top's been cut. It's a little bit curvature in here. Let's run it again. Okay, so whilst that's running, I'm going to show this other one here. So this, go. So I'm unable to change the values and the figures or anything that we've got on this one because of the part that we're on. However, again, if we had the full version, we've got all of the data pretty much to be able to figure out the speed of the air around this part, and you can quite clearly see where there's regions that are potentially going to cause you additional drag on your part, which can help obviously with your simulation. as that's going. So we're pretty much looking at drag here. And I've just put a little bit up in the introduction for this task about the different types of forces that you'll see, aerodynamic forces to have a little look at. So we've got drag. Oh, there we go. It's done. It's 20, 60. And there we go. So it's now taking a projection over that wheel, which is showing quite a drop in, So in the velocity. Okay, so there's probably more of a drop in velocity on this one. However, we've done what all people who are doing any form of scientific test shouldn't do. I've changed the parameters. I've added some wheels in. So we can't fully analyze the data and say this is an improvement or not. Okay. And then finally, let's get the next one running and then I'll come back. Added a spoiler. Just front and rear. So let's run it again. Let's see what's going to happen. Okay, so just going back to this aerodynamics, so we've got drag on the front, which is where the air is getting compressed. We have drag at the back of any overhang from any vehicle, and that will create low pressures of air, which will often swirl. We've got lift that acts on the car, which pulls the car up, and we've got downforce, which pushes the car down. So I don't know if you guys know much about race car designs or car designs and the difference between downforce and lift. Basically, you want a fair amount of lift when you're going straight, because then you've got less friction on the wheels. So therefore, the car should go faster. However, you still need enough downforce to have enough contact with the road, with the tyres. And if you didn't have that downforce and there was loads of lift, then your tyres would just end up spinning. You'd be quite inefficient. When you're going around the corner, you want lots and lots of downforce to be able to push the car down into the road, so you get more friction in your tyres and you can go around the corner faster. That's very simplification, very much a simplification, and that's why trying to remember this. It's not. There's that little flap that opens up at the back of an F1 car. Yeah. So it opens up down the straight, so the car doesn't have as much downforce, so it can go a little bit faster, and then it closes, and then that gives them the extra downforce to go around the corners. That's pretty much a simplification, and it's much more technical than that, I'm sure. That's essentially where we are. Okay, so you can see now that's pretty much the same as the last one. Maybe a little bit of a drop, a little bit more green. And that will come from having these extra bits. Now you can see the resolution on this is quite poor. However, it would be a good place for me to start, just informing my design and where I wanted to go. Ooh. Okay. I did design a couple of enclosures for some electrical components. It was a number of years ago now, and I used this flow control to see how the air would move through the enclosure to see if I had enough cooling. And again, data wasn't perfect, but it just gives you that opportunity to analyze your design a little bit and make a couple of valid decisions off the back of it. Okay, so that's those simulations done. I put a couple of extra questions in here just to pull up a few bits that we'd kind of discussed. So how can the data observed be useful? how can it be considered to be unsatisfactory, this aerodynamic data? How could the simulation be improved? Well, you could have lots more data points for to start with. And then just a couple of considerations then, how could you improve the drag, the downforce, the lift, and therefore the overall speed of that little car? Any questions on that?
No.
No? Good.
So so this is all task B, isn't it?
All for task, that's all task A, but yes, part of task B of the assignment, yes.
Okay.
And then the very final bit I asked just here, as I mentioned before, is then, because we can't apply this at the moment, and hopefully we won't have to, if you could then just consider how some of these, and I put another document up about simulation techniques, just about what ones you could use and what data you could expect to see when you run yours. So I'm just, there we go. I put a little document up on, there we go, simulation techniques. So we looked at a couple of static studies today. There are buckling studies, so you can show where parts potentially would buckle. Frequency studies, so things that have resonant frequencies in. I'm sure you've all done stuff about waves, sine waves, adding waves together. We've got thermal study, which is we can see how the heat would sink into a part that you've designed or not. You can do a drop test study and see if your part will work once it's been dropped. I wish they'd sorted that out for my Samsung S9, which doesn't like falling 2 meters onto a hard concrete floor. We looked at this little optimization design study, and I talked about topology, and this is where the topology comes in as well in optimization. It can also be considered as a generative design. So if you have a couple of bits that you must have, you can use the data to basically design the part for you for maximum strength to weight ratio, for maximum weight loss, that type of thing. There's some fatigue studies. You can do some non-linear studies as well, so how different things will behave in different ways under different types of load. There are dynamic studies to see how the forces from things like motors will behave on your parts. There's a massive motion study as well. We can simulate the motion of lots of different moving parts and see what happens. Composites, fluid flow that we just looked at. And there's also some plastic simulation that's coming in the last couple of years. And you can basically get this to show you where there's optimal positions for runners and sprues. And you can look at the temperature variations as you're injecting parts. This is quite new. This is, I think, this year, or it might have come in last year, just in SolidWorks as well. Okay, so that very last part of that task sheet was to just have a look at some of these methods and see what you could apply to your the parts that you're making or you're designing. Okay.
Yep.
Lots of information. Sorry for that. I've obviously run through it quite quickly, but hopefully that's just giving you a little intro of some of the things that you can do. I think the closing thing for me is on that all of these simulations, they're not highly accurate, but actually for informing design, they can be quite useful. So it's a good thing that they're quick and easy to use, but the opposite side of that is that you don't get that really accurate data out of it. I ran a study. I ran a very similar aerodynamic study on one of these cars a number of years ago, and it took 8 hours to render the results. So although in this basic bit of the software we're not getting great data, at least it's doing it quickly and easily. And I think that's probably all you'd want right at the beginning of a design, unless you need something specific. Okay, any questions?
No.
What's the hand-in deadline then? Same assignment 3.
That's a good question. I think it's a case as soon as possible.
Okay.
But as I said right at the beginning, I've still not got 100% authorization to run this, and for it to cover the criteria. So yeah, it's really dependent on when that comes in. So I would say, yeah, as soon as you can. And I would think probably to fill this in and do this write up, it's probably no more than a couple of hours, is it? Maybe 2 hours work. If that, I don't know.
Do we have a backup plan if they come back and say, no, we can't do this?
The backup plan at the moment would be to get you guys into college to come and do some of this.
Okay.
To actually physically do it. It's a backup plan, which then goes against the government and the college guidance. Yeah. But we have had students in, and I'm in tomorrow actually teaching students, just finishing off bits and pieces with them. So it can be done, but hopefully we can get away with not actually doing it. That would be my preference. So yes, there is a backup plan, but hopefully we won't need to use it. Okay.
Yeah.
Good luck.
All right.
With everything.
Thank you very much.
And I'm always here if you want anything, you need anything. Okay. I always come and check out the team. So if you need anything, just drop me a message. I will get back to you and we'll set up a little meeting if needed.
Okay. So is everything on Teams then? The actual assignment brief?
The assignment, yeah. So I'm still sharing my screen. So let's go to the team. So in the files, I've put assignment 2 folder, design assignment 2. It's got everything in there. So the labs, there's a PDF and a doc of the lab that we've just looked at. There's the assignment brief, which David Gray's edited by the looks on it. There's this design data goes in with this PowerPoint for the evaluation stuff. I just thought I'd chuck my data up that I used, just so you can have a look at that. Quick start guide, the simulation techniques that I just showed you, all the different types of simulation, and then a bit of info about the lab that we just did. So looks a lot of stuff on there, but it's probably not that much, to be honest with you. But yeah, everything's there that you'll need.
So that worksheet then that you just had running by the side, is that as well as the assignment, or can we use that as the basis for the assignment?
That is part B of the assignment. Yes.
Right. Okay.
So you can fill the data in on there. That's why I put those boxes for you to put stuff in.
Yeah.
Or you can separate it and do it in your own format. It doesn't matter.
Right.
I think it's the content that's important.
Yeah, I'd say we can build a project report around it then.
Yeah, so the first half of the assignment is basically what we said at the beginning. We drag the information, drag the data out of our assignment 3.
Yeah.
And then part 2 is just filling out this. Okay.
Yep.
Cool.
Sounds good. Well, I wish you all the best of luck.
Thank you.
Have you guys got loads to do?